Lecture 3, Electricity. The force on the electron in hydrogen. A hydrogen atom consists of a single proton and a single electron. The proton has a charge of T, positive E or electron, and the electron has negative electron. In the ground state of the atom, the electron orbits the proton at most probable distance of 5.29 times 10 raised to the power of negative 11 meter. Calculate the electric force on the electron due to the proton. So this is the circle and this is the electron. Figure 5.15, a schematic depiction of a hydrogen atom showing the force on the electron. This depiction is only to enable us to calculate the force. The hydrogen atom also does not really look like this. Recall figure 5.7, strategy. For the purpose of this example, we are treating the electron and proton as 2 point of particles, each with an electric charge, and we are told the distance between them. We are asked to calculate the force on the electron. We thus use Coulomb's law. Solution. Our two charge and the distance between them are Q sub 1 is equals to positive electron is equals to positive 1.602 times 10 raised to the power of negative 19 coulombs. Q sub 2 is equals to negative electron is equals to negative 1.602 times 10 raised to the power of negative 19 coulomb. The distance is equals to 5.29 times 10 raised to the power of negative 11 meter. The magnitude of the force on the electron is force is equals to 1 over divided by 4 times pi times E node sub 0 absolute E square over R square is equals to 1 over 4 pi times E node sub 0 is equals to 8.85 times 10 raised to the power of negative 12 c square over Newton times m square. So our absolute E is 1.602 times 10 raised to the power of negative 19 coulomb square over the R square is our 5.29 times 10 raised to the power of negative 11 m square. So we're going to substitute, this is the answer, 8.25 times 10 raised to the power of negative 8 Newton. Has part the direction since the changes on the two particles are opposite. The force is attractive. The force on the electron points radially directly toward the proton everywhere in the electron's orbit is thus expressed as force is equals to 8.25 times 10 raised to the power of negative 8 Newton. And V sub significance. This is a three-dimensional system so that the electron and the, can be anywhere in imaginary spherical shell around the proton. In this classical model of the hydrogen atom, the electrostatic force in electron points in inward centripetal direction, thus maintaining the electron's orbit. But note that the quantum mechanical model of hydrogen discuss quantum mechanics is butterfly different. Continued lecture 3, electricity. The net force from two source charges, the three different small charged objects are placed as shown in figure 5.17. The charges Q sub 1 and Q sub 3 are fixed in place. Q sub 1 is free to move. Given, so this is the given. Then Q sub 1 is 2e electron. And Q sub 2 is equals to negative 3e. And Q sub 3 is equals to negative 5e. Negative 5e. And that the distance is equals to distance 2.0 times 10 raised to the power of negative 7 meter. What is the net force on the middle charge Q sub 2? So figure 7, 517 source charges Q sub 1 and Q sub 3 each apply a force on Q sub 2. Strategy. We use Coulomb's law again the way question is phrased indicates that Q sub 2 is our test charge, so that Q sub 1 and Q sub 3 are source charges. The principle of superposition says that the force on Q sub 2 from each of the other charges is unaffected by the presence of other charge. Therefore, we write down in the force on Q sub 2 from each and add them together as vectors. So force is equals to force sub 21 plus force sub 23 is equals to 1 divided by force times pi times epsilon 0 bracket, then Q sub 2 Q sub 1 divided by R square sub 21 J plus the quantity negative n Q sub 2 Q sub 3 over R square sub 23 I. Then we can add this force directly because they don't point in the same direction. F force sub 23 points only in the x direction, while F sub 21 points only in the positive y direction. The net force is obtained from applying the Pythagorean theorem to its x and y components. So force is equals to square root F force square sub x plus force square sub y, where F sub x is equals to negative force 23 is equals to 1 over 4 times pi times epsilon sub 0 Q sub 2 Q sub 3 over R square sub 23 is equals to negative, we got quantity 8.99 times 10 raised to the power of 9 Newton times m squared over c squared, and multiply the quantity 4.806 times 10 raised to the power of negative 19 column multiplied by 8.01 times 10 raised to the power of negative 19 column over 4.044 times 10 raised to the power of negative 7 m squared. So we're going to substitute. So this is the answer, negative 2.16 times 10 raised to the power of negative 14 Newton, and F sub y is equals to F sub 21 is equals to 1 over 4 times pi epsilon 0 Q sub 2 Q sub 1 over R square sub 21. This is equals to 8 our 1 is 8.99 times 10 raised to the power of 9 Newton times m square over c square multiplied by 4.806 times 10 raised to the power of 19 column multiplied by 3.204 times 10 raised to the power of negative 19c over 2 times 10 raised to the power of negative 7 meter square. So we're going to substitute. So this is the answer, is equals to 3.46 times 10 raised to the power of 14 Newton. We find that force is equals to square root F square sub x plus F square sub y is equals to 4.8 times 10 raised to the power of negative 14 Newton. Of angle of is equals tangent sub raised to the power of negative 1, the quantity f sub y is over f sub x is equals to tangent negative raised to the power of negative 1, the quantity 3.46 times 10 raised to the power of negative 14 Newton over negative 2.16 times 10 raised to the power of negative 14 Newton. So we're going to substitute. So this is the answer, negative 58 degrees. That is 58 degrees above the x-axis as shown in the diagram. Significance, notice that when we substituted the numerical values of the charges, we did not include the negative sign of either q sub 2 or q sub 3. Recall the negative signs on vector quantities indicate a reversal of direction of the vector in question, but for electric forces, the direction of the force is determined by the types or signs of both interacting charges. We determine the force directions by considering whether the signs of the two charges are the same or are opposite. If you also include negative signs from negative charge, when you substitute numbers, you run the risk of mathematically reversing the direction of the force you are calculating. Thus, the safest thing to do is to calculate just the magnitude of the force using the absolute values of the charges and determine the directions physically. Continued Lecture 3, Electricity, Example 7.5. How many electrons move through a headlight each second? When a 12.0 volt car battery powers a single 30.0 watts headlight, how many electrons pass through it per second? Strategy: to find the number of electrons, we must first find the charge that moves in 1 second. The charge moved is related the voltage and energy through the equations angle U is equals to Q angle V. 30.0 watts lamp uses 30.0 joules per second. Since the battery loses energy, we have angle U is equals Q minus 30 joules, and since the electrons are going from negative terminal to the positive, we see that angle V is equals to positive 12.0 velocity. Solution: to find the charge Q move, we solve the equation angle U is equals to Q angle V. So this is the formula. Q is equals to angle U over angle V. Entering the values for angle U and angle V, we get Q is equals to negative 30.0 joule over positive 12.0 volt. V is equals to negative 30.0 joules over positive 20.0 joule per coulomb is equals to, so we're going to substitute. So this is the answer, negative 2.50 coulomb. The number of electrons Newton sub electron is the total charge divided by the charge per electron, that is N sub E is equals to negative 2.50 coulomb over negative 1.60 times 10 raised to the power of negative 19 coulomb per electron. So we're going to substitute. So this is the answer, 1.56 times 10 raised to the power of 19 electrons. Significance: this is very large number. It is no wonder that we do not ordinarily observe individual electrons with so many being present in ordinary systems. In fact, electricity had been in use for many decades before it was determined that the moving charges in many circumstances were negative. Positive charge moving in the opposite direction of negative charge often produces identical effects. This makes it difficult to determine is which is moving or whether both are moving. Lecture 3, Electricity, Example 9.5. Current density, resistance, and electrical field for a current coming wire. Calculate the current density, resistance, and electrical field of a 5-meter length of copper wire with a diameter of 2.53 millimeter or 12 gauge carrying a current of 1 is equals to 10 meter ampere. Strategy: we can calculate the current density by first finding the cross-sectional area of the wire, which is area is equals to 3.31 millimeter square. And the definition of current density, Joule, is equals to I over A. And the resistivity of copper, P, is equals to 1.68 times 10 raised to the power of negative 8 resistor, or resistor times meter, where R is equals to P I over A. The resistivity, and current density can be used to find the electrical field. Solution: first, we calculate the current density. Joule is equals to I over area is equals to 10 times 10 raised to the power of negative 3 ampere over 3.31 times 10 raised to the power of negative 6 meter square. So we're going to substitute. Then this is the answer, 3.2 times 10 raised to the power of negative 3 10 cube area over m square. The resistance of the wire resistor is equals to P L over A is equals to quantity 1.68 times 10 raised to the power of negative 8 resistor times meter, and 5 meter over 3.31 times 10 raised to the power of negative 6 m square. So we're going to substitute. So this is the answer, 0.25 resistor. Finally, we can find the electrical field. Electrical field is equals to Pg is equals to 1.68 times 10 raised to the power of negative 8 resistor times m. The quantity 3.2 times square cube area over m squared. So we're going to substitute. So this is the final answer, 5.7 times 10 raised to the power of negative 5 V over m. Significance from the results. It is not surprising the copper is used for wires for carrying current because the resistance is quite small. Note that the current density and electrical field are independent of the length of the wire, but the voltage depends on the length.